Mhm. Okay, so let's get started. Today we'll continue the discussion on World Wide Web that we started last time, but we are going to talk about web caching, cache consistency, and end with edge computing, because a lot of the early work on proxies and so on has actually evolved into edge computing. So this is the picture I had showed last time to introduce the concept of a proxy server and how proxies can also be used to cache. So the top picture here shows a regular browser that is sending HTTP requests to the web server. The web server sends responses. That's the standard client server model. What is shown at the bottom is the client proxy server model. So there's a proxy which is sitting in between the client and the server. The browser requests in this case go to the proxy. Okay, the proxy in this case has a cache. If the requested content is in the cache, then you get a response. And if it's some cache miss, then the proxy gets the content from the server and then sends back a response to the cache, which sends a response back to the browser. So this is an example of a proxy server that is being used for caching. Okay, last time I talked about many other use cases for proxies, but the one that we are going to discuss today is going to focus on caching in particular. Okay, and then towards the later part of today's lecture, I am going to introduce this notion of what is called cooperative caching. It's a concept that can also be implemented using proxies, but it's a more general concept than that. So what cooperative caching says is that there are a set of caches that are working together to act like one big logical cache to requests that are coming in. So when a request comes into a particular cache, you can have what is called a cache hit if that content is already cached, and then you're done. But if it's not in that local cache, the local cache can ask other neighboring caches if that content is cached, and if so, you can fetch it from a neighboring cache rather than going back to the origin, which is where the content would be otherwise. Okay, so here you have an example where you have a web proxy and there's a web server there, but the web proxy initially asks other two proxy caches if they have a content before it goes to the server. Okay, so that's called cooperative caching, where caches cooperate with one another. And we'll come back to how to implement that once we have looked at regular proxy servers and proxy caching first. Okay, all right. So with that very quick background, let's talk about cache consistency. Okay, so the idea here is this is all web content, and these are web caches. So they are storing some sort of web content. It could be HTML pages, it could be images, could be other types of content like audio and video. Okay, but let's just take web pages for now. Okay, so if you have take any web page, it can updated from time to time depending on who the owner of that web page is, and when the content gets updated, then if the proxies are essentially caching older versions of that web page, they become stale. Okay, so you will not be able to serve the most up-to-date web page if the proxy has an older version of the content. Okay, so essentially, the web pages are going to have different update frequency depending on the type of the page it is. If it's a web page for, let's say, news website, okay, maybe there's a breaking stories section or something like that on the site. It may get updated every few minutes or every few hours. On the other hand, if it's somebody's blog, maybe they update it every few days or something like that, right? So the update frequencies of pages can vary from minutes to weeks or even months sometimes if the page is not updated frequently. Okay? Now, our question here is going to be, how can the proxy cache maintain the consistency of cache data? When it changes on the server, you no longer want to stir older versions of that page if they're cached locally, okay? Because then the user sees an old version of the page, so that's going to be a problem. So we want to ensure cache consistency. And about 3 lectures back, we had a detailed discussion of different types of consistency protocols. We are going to look at some simpler versions of those today. Okay? But before I talk about cache consistency, I do want to mention one thing, which is that there are many web pages that are generated dynamically. They are not static HTML files that are stored on the servers. These are called dynamic pages. Okay? And you might also have files that are just HTML that are pre-generated, that are stored on disk. and served web pages. That's called static content. So web content can either be static or dynamic. Okay? When you have dynamic web pages, typically you don't want to use caching because they are regenerated for each request. Okay? And in some sense, you can then personalize the web page also for each request. So for example, you can insert, if you're logged into a site, the web page, the template web page might have your username at the top saying logged in as and give your name. So if another user accesses that exact same page, they'll get a different version where their name gets embedded and so on. So dynamic pages can change on each request for each user, so you don't cache them. Okay? But static web pages, on the other hand, unless they're actually updated by the user or the content creator, they don't change. So you can cache them. So whatever I'm going to discuss today relates largely to static content, whether static HTML pages, or it could be videos or audio data that doesn't change after it's created. Okay? But dynamic content, you don't really cache because there's no point caching it if the next request is going to change it. Okay? So with that in mind, let's look at how do you ensure consistency of cache data. I will talk about two different issues, whether you send an invalidate message to the cache when the web page changes saying that this content has changed, or are you going to send a new update every time a content changes, and we'll see pros and cons of this. The second dimension we'll look at is this cache consistency being handled at the server's end or at the proxy side? Because depending on that, we'll see whether to do it using a push-based approach or a pull-based approach. Okay, so let's start looking at this one at a time. We'll start with what is called the server push approach. Okay? As the name server push suggests, the responsibility of cache consistency is on the server, which means that when the web page changes at the server, it's the server's job to notify proxies that are caching that page saying this content has changed. Okay? So the server has to keep track of all the proxies that have cached any web page from it. Okay? That way, when the page changes, you can then notify the proxy saying this page has changed. Okay? So the server needs to keep some state, which is which proxies have what pages cached at them. Whenever a page is modified, you can notify a proxy. Okay? Now, the notification can be one of two kinds. Okay? You can just send a message saying this web page has changed, remove it from the cache. Okay? That's called an invalidate notification, invalidate message. Okay? Or you could send a new version of the object, which is a web page in this case, directly to the cache, which says here is the web page has changed and here's the new version. So you can then replace the version that's in the cache with the new version. That's called an update message, where you actually send an update to the content. Okay? Now there's a question of, regardless of the whether you send updates or invalidates, what is the right thing to do for a given type of content? Okay? So when should you send an update? When should you send an invalidate? What are some pros and cons? Okay? So let's think about when it makes sense to send one or the other. This has to do with the update frequency of the content, okay, as well as the read frequency. How popular is this page? How many users are trying to access this web page versus how frequently is it changing? Okay? So let's take a very popular page. Okay? So if the page changes at the server, okay, and you simply send an invalidate message, then it's removed from the cache. Okay? But then a request for that web page is going to come soon after, because you said it's popular, so many users are accessing it. Okay? In that case, now that it's removed from the cache has to go back to the server to fetch the new version. Okay? But if you had instead sent an update directly to the cache, okay, then the cache has already replaced the old page with the new one. So when the next request comes, it doesn't have to go back to the server. The new version is already cached. Okay? So for popular content, it makes sense to send updates over rather than invalidates, because if you can always send invalidates, but it will just cause the cache to then go back to the server to refetch that content. Okay? And you could just save that extra message round trip time and the latency by simply sending updates back to the server. Okay? Now the opposite is true for less frequently accessed content, okay, where you can, if you send an update, you send a web page to the cache, but then you consume some network resources, network bandwidth to save it, but maybe the web page is no longer popular. Okay, so it sits in the cache, but no user accesses it, then you just wasted the network bandwidth to save it. In this case, an invalidate would have been better because you just send a short message saying remove this page from the cache, it's deleted from the cache, and if it's accessed at a later time, the cache can fetch it back from the server. If not, then there is no extra work you did by sending an update. Okay, so less popular content, invalidates are better. More popular content, okay, send updates because that will save the cache from having to fetch the page again. Okay. Now, regardless of which of these two that you use, what should be clear is that a server push approach can give better consistency guarantees at the client, because whenever a page changes, it is so the client, the proxy is either notified, the proxy is either notified or you send an update. So you never end up having stale content in your cache and sending stale content to the user. Okay, modular the message propagation time from the server to the proxy when the page changes. Okay, let's say page changes at T. Okay, and then you send an update or an invalidate, it arrives at the cache at T plus delta. Delta is the time, maybe tens of milliseconds. That's the time it takes for the message to go. For that small interval, the proxy actually has older content, but you cannot actually avoid that because you cannot send messages faster than speed of light. So for a very short duration, there'll be stale content. After that, you will have either removed that page or you will have the new version of the page. But regardless, if you ignore the message propagation delay, this is a strong consistency guarantee because you are not keeping stale content in your cache. Okay, so big advantage of the approach is it provides tight consistency. It's not strict consistency because, as I just said, strict consistency would have meant as soon as the page changes, instantaneously you have to tell the proxy, but there is no way to do that. You still have to pay for the time it takes for a message to propagate on the network to get to the proxy. So it's tight but not strict. For a minimal stale data. In this case, the intelligence of cache consistency is at the server. Okay, proxies can be passive, they don't have to do anything. They will be told when the content has changed, or they'll be sent new web versions of the page. Okay, so proxies can be relatively dumb, the servers have to be more intelligent. Okay, so those are advantages. Disadvantages is you have to keep state at the server. Okay, you have the server has to, what is the state? The server has to keep a list of all the proxies that, and then which of these proxies have what web pages cached at them. Okay, because whenever any of the pages the server has changes, it has to send a message to the proxy. So you have to keep this state. Okay, and potentially you have to keep this state for a long period of time because you don't know when you can remove a proxy from that list. So potentially you could have to store this indefinitely. Okay, so the state that you have at the server can keep growing over time as new proxies fetch web pages from the server, they get added to the list. So this list keeps on growing. Okay, that's a problem because fundamentally HTTP is a stateless protocol. HTTP does not by itself require the server to keep any state. So adding this state will require you to use mechanisms that go beyond HTTP to implement server push-based cache consistency. Okay, so you can't do this just with HTTP. And we'll see some ways to deal with this, and the state may need to be maintained indefinitely. If the server crashes and comes back up, if the state was kept in memory, the state is gone. So then when the server reboots, you don't know which proxies have what content, so you can no longer send this message. So state actually has to be stored on disk, which introduces additional overheads. Okay, so those are some pros and cons of a push-based approach. Any questions here before we look at the pull approach? Okay, so the pull approach is the opposite. In this case, it's a proxy pull approach. As the name proxy pull suggests, the intelligence of cache management is now embedded in the proxy, and it is the proxy's job to keep track of what pages have been modified, which ones to remove from the cache, and so on. So the proxy is entirely responsible for maintaining consistency. How does the proxy do this? The proxy has to keep polling the server. So this is also called a poll-based approach, POLL, which is the same as a pull-based approach. So you poll periodically the web server saying, has this page changed? You will get either a yes message or you will get a no message. And the way you can actually do this is you can use HTTP to poll. Okay, because HTTP, you all know HTTP as a get message, right? So this you know. Okay, but if you actually look at the HTTP protocol, there is you can add conditions on the get, which is called a conditional get. Okay? You can say, so one of the conditions you can have is something called an if modified since with a date and time. Okay? So you can say, get me this URL, but only send it to me if it has changed since, and you specify a date. Okay? So what you can do is you can see when you brought the version of the page into your cache. Okay? And then you can ask, has it changed since I fetched it? Okay? And the server can either say no, hasn't changed, and there's nothing to do, or it can say yes, it's changed it, and then the get will get you a new version of the page. Okay? So you are sending get messages, but you are retrieving the page only if it has changed, as opposed to standard get, which will always get you the page. Okay? So you can use if modified since. They are called IMS messages. IMS for which is if modified since. IMS HTTP get messages to essentially poll the server. So this can be done with standard HTTP. You don't need anything else, because all this proxy is doing is polling by sending HTTP get messages or conditional get messages. Okay? Is that clear? How you are maintaining consistency? Okay. So now the question is, how frequently should the proxy ask the server? That's really the problem, right? Because you don't know when the page changes. All you can do is you can find some period to poll the server. You can say, I'm going to poll aggressively every minute. Okay? But maybe this page doesn't change very frequently. It could be somebody's blog, they change it once a week. Okay? And here you're checking every minute, and all you're getting is, no, it hasn't changed messages from the server. You waste a lot of network bandwidth and are not getting any real request from the response from the server saying it has changed. Okay? Or you could say, I'm going to be very lax, and I'm going to poll once a day. Okay? And then it used to be a news website that's changing once a minute, and you have now a stale content that stays in your cache for over a day or up to a day, and you're sending this stale content to all the users that are asking for this page, and they're seeing old versions. Okay? So neither is reasonable. So you don't actually know, and the proxy doesn't know how frequently to poll the server. Okay? So there are ways to address this, which might make it a little bit easier. One is the server can assign what is called a time to live value, or a TTL. A time to live value is some estimate from the server side as to when the page might change next. That's the lifetime of the page. That's why it's called time to live. Okay? So the server could, whenever you do a get, the server could attach an expiration time or a time to live, saying, keep this in your cache for whatever, 6 hours, okay, or 1 hour. Okay? So the proxy could then wait for that TTL to expire and then poll the server, because the server gave you a hint, and then you can poll the server. That's one approach. Okay? But there's no guarantee that anything that the server told you is actually true. Because the server might say, I put an expiration time of 6 hours, but it's user's web page. Maybe it's their blog. They can change it whenever they want. So the server doesn't actually know when the page will change. It's just a guess on the part of the server, just to provide the proxy some notion of when to poll next. Okay? So time to live approaches are just heuristic. There are no guarantee that the page will not change until that TTL expires. It could very well change, and then again you have stale content. Is that clear? Okay, so push-based approaches are so easy to implement at the proxy, but they have weaker consistency guarantees than push-based approaches, because if the page changes, you will have stale content in your cache until the next time you poll, whenever that is. Okay? And then how frequently to poll is not clear a priori, okay? Because you don't know the frequency of updates of a page. So you might poll less frequently than you need to, and then your stale content. You might poll too aggressively, and you are just wasting network resources. Question there. Okay. Okay. Question is, pull is simpler, but push has better consistency guarantees. Can we do both? Why can't the developer then decide, or maybe the proxy decide dynamically? So the issue with push is the server has to support it. Right? If it's just a standard HTTP server, it will not have push functionality built in, So in that case, you have no choice but to use pull. Okay? If the server actually has additional functionality to do push, or let's say you have HTTP2, which I introduced last class, which actually has built-in push functionality that you could use to implement cache consistency, then you can do this. But there's no guarantee the server has push ability at all, in which case you are stuck with this. Okay? But we'll see a hybrid approach that tries to combine them in just a second. Okay, let's talk about how do you decide this polling frequency. Yes, question.
Take additional load of just answering the client that if it has the updated content.
Yes. Question is, in the pull-based approach, does the server have additional overhead because of this extra if modified since HTTP messages? That is absolutely true, right? So you will have extra overheads in pull-based approaches because you might have to make these checks frequently if you want to keep your cache fresh, and that introduces additional load on the server. Okay, and which in the push-based you didn't have to do that. The server sends you a message whenever the web page changes. Okay? Does DNS use the pull-based approach? Is that the question? So the DNS is a pull-based protocol, and that DNS does use host name to IP address translation, right? So you say www.google.com, and you look up that DNS. DNS sends you back an IP address. Okay? So that part is pull-based. Okay? DNS also uses caching. So there are the resolution is cached at various levels within DNS servers, and how to maintain that consistency, that's a different problem. You use time to live values in DNS. There is no checking that has this IP address change because IP address don't change that frequently, unlike web pages. But having said that, it is a pull-based approach in that sense. Okay? All right. So can we do better in terms of allowing the proxy to figure out how frequently to poll a web page? Right. So that's the question. And then here is one idea of what we call intelligent polling. So here the proxy can dynamically decide the refresh interval. Okay? Here's how it will work. It's a completely empirical method. So let's say when you first fetch a new page into the cache, you know nothing about this page as a proxy. So you will start with an aggressive polling interval. So you'll poll every minute or every 30 seconds. So you ask the server 30 seconds later or a minute later, as the web page change, you will get one of two answers, yes or no. Okay? If it's a yes, then that's good because you chose an aggressive interval and looks like the page is changing frequently. At least it changed frequently once, so you get the new content or invalidate one. But if you get no, then you say, okay, I just wasted a message by asking the server and the page hasn't changed. So the next time around, I make the interval longer. So I go from, let's say, 1 minute to 2 minutes. I wait for 2 minutes and ask the server. If it says no again, then I increase that to 4 minutes. I can increase it in any way I want. So this one is multiplicative increase where I'm increasing by my multiplicative factor. So I can keep increasing it until I find the refresh frequency. Maybe it's a day, but eventually this poll interval will keep growing. And then at some point, you'll find that the web page actually changed. And then you now know that it actually changed out maybe X time intervals after I fetched it. That could be 1 day or 12 hours or whatever it is, right? So I can then try to see if the next interval happens at that frequency. And if page has changed, maybe I should try to reduce it a little bit just in case I missed intermediate update. So I can keep changing the poll frequency based on what the response from the server is. Whenever a web page changes, I make the frequency lower than what I had so that I don't miss any updates. But then if there are no updates, I keep increasing it. Right? So this is essentially this approach. So you start with a conservative refresh interval. I increase the interval if the object has not changed between two successive polls from the proxy, and I decrease it if I essentially find that it was updated. So this will automatically discover, okay, empirically the average refresh rate for any page. Okay? For pages that are changing frequently, you will find that it is changing frequently, so you'll keep polling frequently. For pages that are not changing frequently, the polling interval will keep growing because that's what the approach does, and I will poll less frequently. This way, your proxy does not have to a priori decide a fixed interval. But the other approach would have been you just configure an interval. You say it's 6 minutes for every page, 6 hours for every page, and that's what you use. But that doesn't work for different pages because they have different update dates. Okay? So this approach can allow you to figure out, regardless of which server has it, what type of content it is, how frequently to pull. Because so this is going to save your network resources by not wasting them. Okay? But it still does not guarantee you that a page will not change between successive polls or anything like that. You still have the weak guarantee where the page may have changed and you will not discover it until the next time you poll. Okay? So it's an adaptive approach. It adapts the poll frequency to the update frequency of the page, but still guarantees are not going to be any stronger than what a pool-based approach generally gives you. Is this clear? Okay. So advantages, disadvantages. Again, pool-based approaches, you can implement this using standard HTTP. You require no additional support from the server, unlike push-based, which has to support push functionality at the server. Okay. This can be done with any server that supports HTTP, which is every web server, because you are just using conditional get and IMS messages. The server remains stateless. Server doesn't have to keep any state. Okay. The proxy is just asking for poll messages. Okay. It is resilient to both proxy and server failures. The server, there's no state, so there's nothing to do. Proxy can fail and come back up. And then all you need to do is just start polling at an aggressive frequency for every page and then start reducing that interval for pages that are not changing. So the proxy doesn't have to keep any state at all. Okay. Disadvantages of the approach, weaker consistency guarantees. Okay. You can have stale content in your cache, and all user requests for that page will get stale as in an older version of the page until the proxy refreshes it. Okay. Strong consistency is possible in a pull-based approach only if you poll before every HTTP request from a browser. Okay. Browser sends a request to the proxy has it cached. You send a IMS message to the server, first check if it has changed or not before responding to the client. Okay. This will guarantee that you will never send any stale content to the server, to the client. Because before responding after a cache hit, you are checking whether the page changed or not. Only then you respond. Okay. But clearly, although that approach gives you strong consistency even in a pull-based approach, there's a problem. Okay, what is the problem? Okay, there is an overhead. Can you be more specific? What is the overhead? Yeah. Yes, exactly. So for every request, if you have to ask the server whether the page changed, you may as well not had the proxy at all, because you are putting a proxy to reduce load on the server, so the proxy can answer some of the load from cached content. But here you are asking the server anyway after every request comes in, so that does not reduce the load on the server. It increases the overhead back to what it was without the proxy. So you may have as well not had the proxy. So it's a good approach in giving better guarantees, but not a great approach in terms of saving any overhead at the server. Yes. Yes. So yeah, so the question is it's not as bad as what I said before, because here you're only sending conditional gets as opposed to actual gets. That is true, but you have to also realize that the latency of responses has gone up. You put a proxy usually at the edge of the network so users can get content faster. Okay? There are two advantages of proxy. You keep them closer to users so you can get content faster. And then also the proxy absorbs some of the load, so the server sees a lower load. Okay? Here the server load has gone up, but not as much as getting pure get. You're right. But the latency advantage has also gone away, because the latency now is actually the latency to go to the proxy. The proxy still has a round trip to the server. So users are not seeing any faster page load times. Okay, so that is not going to, that advantage goes away. So you're right. I think the load is not as high, but the latency increase is still not something you want to deal with if you could avoid it. Okay? So that's a disadvantage. It requires more intelligence at the proxy to poll more intelligently. As I said, if you do some simple static polling based approaches that might actually result in either high overhead or invalid or content that's not fresh. And as I said, the message overhead is strictly higher than server push. Okay, in server push, for every time a page changes, there's one notification that goes to every proxy. Okay, so one update, one message, because that's the notification the servers. In a poll-based approach, the overhead could be arbitrarily high depending on your polling frequency. For every update, you might have, maybe the update is every hour, you decided to poll every minute. So there are 60 messages for every update. Right? So as opposed to the optimal, which is the server push, where every update triggers exactly one message. That's the least you can have. Right? So you have to notify the proxy. So there's one message at least, but a pull-based can have arbitrarily high overhead depending on your polling frequency. So this will have higher overhead than a pull-based approach. Okay, yes.
Pull-based approach, how does the proxy know like which server has the ability?
Okay, question is, in a pull-based approach, how does the proxy know which server has the updated content? The way you would keep that information is for every web page you have cached, you also keep the URL of the page, okay, which is the same information the browser has. The URL has the name of the server and the full URL. So you can just send a GET request with that URL and you'll get a page back from that server. Okay, the server name is embedded in the URL. Okay, so just like any standard URL that you have. Any other questions here? Okay. All right. So that's pull-based approach. Let's look at a hybrid approach that tries to combine the best advantages of both of these approaches and try to reduce some of the disadvantages. So this approach is called the leases-based consistency approach. But let me explain what a lease is, then we'll see how to do lease-based consistency. So you probably heard the word lease, right? If you rent an apartment or rent a house, you signed a lease, which is a rental agreement. And the rental agreement has a duration. That's the duration of the lease. Okay? So the more general term here is a lease is basically a contract between two parties for some duration of time where there is some agreement on what happens during that time. Okay? That's what you think of as a lease in the physical world. That's the same thing concept you can use in a distributed system. Okay? So what is this in the context of consistency? So essentially, in this case, when a proxy first fetches a copy of the page, the server not only sends the page, but it also sends a lease with the page. Okay? And the lease is for a fixed duration. And that what the server says is for that duration, it will agree to send push-based messages if the page changes in that time. So you can say, here's a lease for 6 hours. If the web page changes anytime between now and 6 hours from now, you will get a notification. Okay? So now the proxy knows that so long as it has a cached page with an active lease on it, the server is now responsible for telling it that the page has changed. It does not need to hold the server. Okay? So until the lease is active, this looks like a server push. Because that's what server push did, with the difference being in server push, you can think of a server push as a push-based approach with infinite lease. But there was no duration. The server had to keep sending notifications forever effectively because there's no way for it to know whether the proxy was interested in this or not anymore. Okay? In a lease-based approach, once the lease expires, it's now the responsibility of the proxy to decide whether it wants to renew the lease or not. Okay? Maybe the page is no longer popular. The proxy may decide it will just invalidate the cache, and let the lease expire. So the server no longer has to send notifications for a web page that is no longer being accessed by user. That's wasted resources. Okay? But on the other hand, if the proxy is continuing to see requests for this web page, it can say, let's renew the lease and keep getting notifications and the content stays fresh. Okay? So basically now both server and proxy have to participate here. Okay? The server has to keep sending notifications until the lease is active, and then it's the proxy's job to decide whether to renew the lease or not, okay, depending on whether the page is actually being accessed or not. Okay? So now the duration of the lease allows you to control, okay, how things work. Okay? So, but before we do that, here's a picture that explained whatever I said here. So there's a client there. it sent a read. Read is essentially an HTTP GET request to the proxy. Okay? Proxy is sending a GET request plus a lease request to the server. The server sends an HTTP reply, but with a lease of a certain duration. Okay? And while that lease is active, you can keep getting invalidates or updates, or the proxy will not have to worry about is this content fresh or not. It can continue to serve requests for it. Right? So that's the lease-based approach. Now, question is how long should the lease be? Right? So that will actually give us various properties. And if you think about it, if you send a lease of 0 duration, this is actually a pull-based approach, because lease comes in, it immediately expires. Now, either the proxy has to renew it or poll saying that I want a new copy of the page, because as soon as the lease expires, the page may no longer be valid from the proxy's perspective. So this degenerates to a pull-based approach if you put a 0 duration or a very small duration. If you put an infinite duration on a lease, it becomes a pure push-based approach, because now the proxy is just sending you updates all the time, or the server rather is sending you updates all the time or notification. The proxy doesn't have to do anything. Right? Anything in between gives us different properties, and we'll talk about how to decide the lease duration. Any questions on this before I talk about determining durations? Okay. So the reason it's hybrid is you can see that both proxies and servers participate, and depending on the lease duration, it looks like some combination of polling and server push. Okay? But let's talk about how to decide lease duration. You can say the lease duration is based on the lifetime of objects, which is how frequently the object changes. Okay? You could say if it's a more popular object, it's changing frequently and it's popular, give longer leases, because you might have to send a lot of notifications or keep the content fresh. Okay? If it's not, the age has, the page has not changed in a while, age is long, you can say, I don't need to send notifications as frequently because page is not changing. So you can get away with shorter leases. Okay? The other thing is you can look at proxy's popularity to decide how long the lease should be. If some pages are very popular at the proxy, you can say maybe it's worth sending notification because the page is being accessed frequently. So give longer leases. Right? But if it's not popular, why bother sending notifications? You can get away by giving a short lease, letting it expire, then let the proxy decide whether it wants to renew it. Okay? Now, one thing I should say here is the popularity of web pages tends to be very skewed. Okay? This is why some of this makes sense. There are some web pages that are really popular, okay? But there's a long tail of web pages where they're really unpopular, okay? Meaning that they're rarely accessed. Okay? So it's not uniform distribution. It's actually tailed, what is called a zip distribution, a ZIPF, Zipfian distribution, which basically looks like some content is very popular and there's a long tail. So think of it as a 80-10 or 90-10 rule, where 90% of the requests go to 10% of the pages. Okay? And then the remaining 90% of the web pages see the remaining 10% of. So that's the type of access you see in any web system. Okay? As a result, you want to treat what is called popular or hot content differently from unpopular or cold content. You don't want to treat all web pages the same way. Okay? That way you say have more efficient system design, which is why a popularity-based lease actually makes sense. So you are keeping all your network resources to send notifications for the more popular content. Those are the ones that users are seeing. That's what you want to ensure is actually fresh at all the proxies. Okay? So that's another policy. Third policy could be load-based. If the server load is high, you could say you are going to actually use shorter leases, because as we said, whenever you have notification, that's additional messages the server has, and or the load is low, you can give longer leases. So there could be many different policies, okay, that you could use. The renewal frequency base is a good one to think about. So long as there is some estimate of the popularity that the server knows about, it can tailor the lease duration based on how popular the content is. Okay, is that clear? All right. So those were single proxy based approaches. Okay? One proxy, one server. Now we'll look at multiple proxies, okay, which gets us to this problem of cooperative caching that I just introduced at the beginning of the class. So the way you want to think about this is when you deploy caching-based infrastructures, you are going to put multiple proxies at different network locations. Okay, so maybe let's say you have an organization like UMass, you can put one proxy in the computer science department, you might put one in the electrical engineering department, maybe one in some other department or college, and so on. And the local traffic first hits that proxy before it goes to the server. So you are deployed more than one proxy to accelerate the GET request. But then these proxies can actually form some sort of a structure where they decide to work together, not just as independent proxies. Whatever I talked about previously, the lease, the server-based, server push, proxy pull, they are all independent proxy-based approaches. The proxy does not know about other proxies in the system. It doesn't communicate with them, but you could make them all cooperate. Okay? And so the way they're going to cooperate is when a request comes in, you first check your local cache. If you don't see a hit, you can check some other nearby caches. If no one has it, then you go to the server. Okay? That's the basic idea. I'm going to show you an animation of this with a 4-proxy system. Okay? So you have the server at the top. Okay? You have a parent cache here, and then there are 3 leaf caches. So this is a tree-based hierarchy, and there's 1 root and 3 children. Okay? So simple tree. Okay? And there are some clients at the bottom. There are some open source software that uses this type of architecture. There's one called Squid that's open source, very popular. Another one called Harvest, which kind of died, but it still was an open source system that used a similar idea. Okay? So now let's take a client that requests a content. Right? So here is a client that sent a read, which is like a GET request to a cache. Okay? So if it does not have that content, if it has it, then you're done. You would have sent a response. But let's say it doesn't have it. So in this case, you're going to send request to your other peers as well as your parent. Okay? And you send these messages called ICP messages. ICP means Internet Cache Protocol. Okay? So essentially, every time you have a local miss, you ask all the other peers on your level of the hierarchy as well as your immediate parent node. And there could be multiple levels of the hierarchy. Here we only shown one. Okay? And if any of them have it, you're done. Okay? But let's say nobody has it, so they all get and said no to this cache. We don't have this content. And then you are going to send this forward this HTTP request to your parent where that will recurse. If there was another hierarchy, this parent would have asked all of its peer and its parent and so on. Okay, no question there? Okay, question is why are we using ICP as opposed to HTTP? Is that your question? Yeah. So HTTP is not designed for cache consistency, right? So they developed a companion protocol for web caching, which they called ICP, but it's basically asking whether you have the content, not have the content, etc. Okay. The overhead be same. It's not very different from HTTP, but it's designed more for caching as opposed to interactive web browsing and things of that sort. So it's just a way to ask for some content and fetch the content. Okay, so not very different from that perspective. Okay. So in any case, here, since the peer cache said no, they didn't have the content, you sent it to the parent. The parent obviously doesn't have this content, so it sends that HTTP request to the server, which has it. Obviously, then the server sends a response. The response comes back to the cache. Cache will then forward that back to this user. Okay. Yes, question.
What if for cache proxy version of the
Okay, question is what if the first proxy has a different version of that same file, meaning an older version? Okay, question is what if they have different versions of the file? So in this case, the assumption is that if anyone has the content, you are going to essentially send that content, okay? And you want to maintain the consistency of that content. So if the content has changed and any proxy knows that it has changed, it can inform other proxies saying this is the latest version. So hopefully the ICP protocol will take care of not having one version that's 3 hours old, another version that's 6 hours old, and all the caches seem to have different versions. That will cause problems. Okay? So if you fetch a new version, then you can also notify that this is the newest version, so invalidate old version. So you could do all of that. Okay? All right. Now, I think if you see this protocol, you will understand now the problem with this approach. Okay, so if you have what is called a global miss, which means that you ask for a web page that no proxy has, okay, you see that there are lots of messages that are going back and forth before the user gets their web page. Right? The user just clicked on a link and they're waiting for the page to load, and the proxies are communicating with one another, forwarding the request, it keeps getting forwarded, and then eventually a response comes. Okay? So from a user's perspective, the page load time has increased significantly for a global miss. Okay? If you had a local hit, which means that the nearest proxy had the content, then you get it immediately. That's faster than going to the server. Okay? If one of the nearby proxies has it, still faster. Okay? But if no one has it, it was much faster for the client or directly gone to the server to get the content, then send this request to the proxy hierarchy and have them request the content for you. Okay? That has significantly slowed everything. Is that clear? That I mean, there's a issue here. Cooperative caching is all good, but occasionally when no proxy has the content cached, things are slow, quite slow. And if you had multiple levels, this would be even slower. Right. So let's try to think about how to address this problem. Okay. Here is a different approach for trying to do cooperative caching. Okay. First thing we do is we'll remove the hierarchy, because hierarchies are adding overhead. Every time you have to send the request up the chain, it's adding more and more hops, and each hop is adding latency to a request. So we don't want hierarchy. So it's a flat structure where the proxies are cooperating with one another, but if they don't have the content, they directly go to the server. So misses will mean either you have it, otherwise you go get it from the server or something like that, right? So that's the first thing. But the second thing is you also want to reduce the overhead of querying other proxies to see if they have a page or not. Okay? You want to cooperate, but in the previous approach, if you didn't have the content, you simply sent ICP request saying, do you have this page? And you waited for a response. Okay? How can we reduce that overhead? What could we do that reduces the overhead of querying other proxies? Thoughts? Okay, so you can have a central state manager for all of the caches. That manager keeps track of what is cached where. Close, but we don't like centralization. So you want to keep extra information. Okay? It's just state information. And essentially what you will have is that shown here. Each proxy will know what pages are cached locally because it knows what it has cached. Okay? What if it kept a table of what pages are cached at other proxies as well? Okay? So you now have a table saying these are my web pages. Then you keep another table, database, whatever it is, or hash table that says here are web pages cached at nearby proxies. So now a request comes in, you just do a hash table lookup saying is this page cached at my cache? If not, you look at the other table saying is this cached anywhere nearby? The answer is no. Then you just go to the server and fetch it. You didn't ask other caches and have them tell you no, then you go to the server. It reduced you the overhead or latency of asking other caches because you're keeping information about every other cache in the system. Okay? And that table is not going to be high overhead. I mean, maybe it will have million entries, but that's still not bad. You can keep that in my main memory if you want, or it certainly could be kept on disk. So you are going to essentially keep track of a hash table or some table that keeps tells you what each proxy has in the system. Okay? So what does this mean? Okay? Lookups are always local. Right? You don't need to ask anyone. You're just going to do a local lookup to decide does somebody have it or should I go to the server? Okay? Somebody could be that local cache or some nearby cache. A hit is at most 2 hops. Okay? So essentially, either it's a local hit, that's 1 hop, the client sent you a request, you send a response, done. Okay? Or you send a request, okay? You say, okay, that's A is at node X, which is here. So then you go get A, and then you get a response, and then that's 2 hops. Okay? So which would basically increase the latency some, but that's a nearby cache. Hopefully it's nearer than the server, so that's still fast. Okay, and then you have a miss, which is shown in this picture. Here you ask for B. B is not in the table anywhere, so you just get it from the server. You're done. That's also 2 hops. Okay. Now you can have a problem where your table is not up to date, right? So you have here an entry that says web page A is at node X. So you probably say, I get a read request. I say it's at node X. I send it to X, but X may have invalidated the page. Okay, or it may have said this page is expired, so I remove it. So that basically means now there's a remote miss, not a local miss. That requires I to go back to the server and get. Okay, which is why miss is at most 2 hops. Okay, normally a miss is just you just get it directly from the server. But if you make a mistake, because the table has to be kept up to date, but sometimes it may take some time for other proxies to notify you that they deleted a page from their cache. If that happens, there's not big harm done. You will just have an extra hop before you get the page. Okay? Still not as bad as our hierarchy. And those types of misses are hopefully rare, that they don't happen frequently. Okay? But it also says that this table that you keep has to be kept up to date. We need to have current information about every proxy. Whenever that change, you get new pages, you tell others. You throw out a page from your cache, you tell others. And if there's a little bit of delay, you might have an extra miss that happens as well. Yes, question. Yes, so question is, do you enforce the miss by forcing it to go to 2 hops is the most you will have, because there is no re-forwarding, right? So you get a request, you either serve it locally. If nobody has it, you go to the server. If you think someone else has it, you send it to them. If they have it, you're done. You get the content. But if you sent it by mistake, then that cache has to go fetch it from the server. It's not going to forward it again. Yes. So you don't forward twice in this case. You only forward once, because that miss is if you get a request from the cache, you don't do a table lookup to see if somebody else has it. You only see if you have it. If you get a request from the client, you can say, do I have it or does somebody else have it? So you treat these requests differently. That way the forwarding does not keep propagating. Okay. Is that clear? Yes. Okay. Question is this going to be more efficient than the previous approach? Because after every cache update, you have to inform all the other caches. That's your question, right? So there are 2 things to keep in mind. First thing is the caches are not going to change that frequently. Okay? You fetch a new page less frequently than you are getting HTTP requests. There are many requests, but page fetches might be less frequent. Okay? So these update messages are not going to be that frequent as the other one. Second is the update messages are not in your critical path where the user is waiting for a response. The updates are happening in the background. Really, you don't want, you put a proxy so users could see faster load times. If after putting a proxy, you slowed down the user's page load times, then that defeats the whole purpose of proxy cache. These updates are not actually slowing any users down, because at most the users are going to still see a local hit, or they go get it from the server, and that's still okay. And then the updates can happen in the background. That doesn't change anybody's load time and so on. So the overhead is not as in the previous case, the overhead was happening when users were requesting content. Here, the updates are actually happening when the proxy fetches new content, which is at a different frequency altogether. Yes, there is an overhead of updating the table. We should not discount that overhead. But all I'm saying is that the message exchanges here for cache consistency are less frequent than in the previous case. Okay? And furthermore, the more important part is we did not slow down the user as much. Only time you did that is when you made a wrong guess, because your table was not up to date, hash table was not up. But that hopefully doesn't happen as frequently. Okay. All right. So that is web caching. And so that brings us to this essentially how proxy caches have evolved into this area that's now called edge computing. Edge computing basically means that just as the proxy caches were deployed close to clients, which is called the edge of the network. Okay, so the edge of the network is where clients connect to the network. Okay, so this has led to a paradigm called edge computing, where you put server resources close to users. Okay? And these servers can provide various types of useful services. The servers could be proxies in many cases, okay? Or they could be regular servers as well. Okay? So it could be either a proxy server or just a standard server. The main difference is, rather than putting it in a cloud data center, which is far away, you are putting server resources at the edge of the network close to the user. So you can use these types of servers to do low latency computing. Any type of application that requires fast response time, low latency responses from the server, benefits from edge computing rather than cloud computing, which might require you to go to the nearest cloud region, which will still not be very close to you. Okay? It may be 30, 40 milliseconds away from where users are, as opposed to 5 milliseconds away, which is very close to where you are. Okay? So this will significantly lower the latency as compared to remote cloud servers. Maybe you have higher bandwidth because you're not going on a public internet. It's just the client going to a very nearby server, which might be close to you, maybe even on the same enterprise LAN or something like that. So you might have bandwidth advantages. And sometimes if the network somewhere gets partitioned or the cloud fails, you still have local servers that are allowing you to access this service or application. Okay? So this approach really is not an alternative to cloud computing. It's a complement to cloud computing. If latency is not a consideration, okay, by all means, you should use the cloud. Okay? Because there are plenty of resources, large data center, okay, you can get resources for cheap and so on. But when latency is a big consideration, okay, then you can use edge resources. Okay? And many times cloud providers are themselves offered edge servers as an additional offering, saying if you need nearby servers, use these edge servers. If you are okay with standard cloud servers, you can. So cloud computing companies have also gotten into edge computing as one of their offerings. Okay? But regardless, it should be clear that there's a distinction between the edge and the cloud. Cloud servers are remote. Edge servers are also remote, but much closer to the user. Okay? Or cloud is more distant than the edge. Okay? With that background, let's take a little look at how this area evolved. So it actually arose from two different subfields of computer science. One was mobile computing, okay? Other was web caching. Okay? The web caching you can probably see already. Okay? You can think about, there were initially users companies started deploying single caches at the edge. Then they decided, let's put a network of caches, do cooperative caching. And they said, why don't, then there are companies that came about. They said, we will deploy a worldwide network of caches, and you can then go from anywhere in the world to your nearest cache. That was called content delivery networks. Okay? So they basically took this idea of web caching and turned that into a commercial offering. So they went and deployed caches everywhere. And that basically, then they said, why just stop at doing caching? Let's use these servers to do other computation. So that got you to edge computing, where they use their proxy caches or proxy servers rather, which initially were deployed as caches to do other things. Okay? So now you could essentially do local computations at your proxy for the application or the user, rather than just cache content for the user. Okay? That was one evolution of edge computing. Okay? There's a whole another area of mobile computing which also gave rise to edge computing, and there was a different reason. Okay? So these were users who had mobile devices. Maybe they were laptops from 20 years ago, 10 years ago, or phones, early smartphones. Okay? None of these devices were that powerful. Okay? They had limited battery life. Okay? So if you did a lot of computation locally on your device, let's say on your phone, the battery will die. Okay? But if you could run the application close to the user, okay, close to the user's phone, in this case on the edge server, okay, then you could reduce the computational load on the device. First of all, phones didn't have powerful processors, so it was limited by how much computation you could even do. So you could offload the computation to a nearby device or nearby server, and also save battery life. Okay? So you can get more powerful computations done, even though your device had limited computation. Okay? This was called computational offload, computational offloading. So you're offloading computation from a less powerful device to a nearby server. Okay? So that idea of computational offload gave rise to edge computing, because there were lots of reasons to do edge computing. Okay? In today's world, you can think of phones are powerful, laptops are powerful, but now you start seeing all these VR headsets. Okay? Apple has one, it has limited battery life. If you run a lot of compute on it, the battery life will go down even more. Okay? So rather than doing all the computation on that device, why not run some computation locally on some other machine, okay? And then just have it send you results. So you save your battery life, because more computation means the battery is going to not last as long. Right? So you can always find lower end devices that can actually benefit from using computational offload as an approach to using more resources or to save energy for battery life. Okay? So this area also gave rise to edge computing. So between these two areas, I think eventually edge computing became more of a commercial offering. But these were the reasons why this field has actually come about. Okay? So if there are no questions on this, let me explain now content delivery networks, and then I'm going to talk a little bit about edge computing as it actually is seen today. Okay? So content delivery network, I just gave already a brief introduction, but these are networks that have lots and lots of caches that are deployed on very large scale. Okay? That deployed all across the internet. The larger companies like Akamai, for example, which operates a very large content delivery network, have 120,000 servers deployed, okay? All across the world in more than 1,000 different networks in 80 countries. No matter where you go, there is some edge server that is close by. So if you are using Akamai's network to deliver content, okay, it can actually give you very fast load times. It can dramatically reduce load on servers and so on. Okay? Now, although Akamai initially, the content delivery network started by hosting web pages and images and so on, today it's actually being used to deliver things like streaming video. Okay? Because video is now the more heavy duty content. If you have a single server that is trying to send a lot of video stream, that gets overloaded. So the idea is you take all these videos and then you put them in the caches and deliver them from cache. Okay? Practically every streaming service that you have today, whether it's Netflix or Hulu or even YouTube for that matter, they don't actually deliver content from their servers. They will often push the content to caches and deliver it from cache. That actually increases the capacity of the overall delivery service. Otherwise, your servers will get overloaded. If it's let's say a popular movie comes out, everybody tries to watch it, server gets overloaded. But you cache it at tens of thousands of caches and deliver, each one delivers a small number of users, that's fine. That scales very well. Okay? So it is essentially how you can take any rich content, okay? Not simple text pages. That's not really something you can use for content delivery, but any rich content, larger images, audio, video content, CDNs can do a very good job of trying to deliver that content. Okay? Now, how does it work? So here is what you essentially do. So you can, as a content provider or a web server provider, you have to essentially sign up for content delivery service, and you get to decide what content you want to cache. Okay? It's not that the CDN will decide, I will cache this content for you. So the way you are going to do this is, in your web pages, you are going to embed links to the CDN content. So you will say let's say cdn.com foo.mp4, and that a movie will then come from the cache as opposed to coming from the server. Okay? So here is how things are going to work. So I'm going to show you a picture, and then I'll come back to request routing. Okay? So here is your client in the middle. Okay? There is a CDN server here. Okay? That's one of the many hundreds of caches. Okay? This is just one, but think about hundreds or thousands of them. That's the origin server. So there are three things. That's your client. That's the proxy, one of many. And here is your server. Okay? Now, the client is first going to go to the server, okay, and get, let's say, an HTML page. Okay? That page is not cached. That's coming directly from the server. But within the server, within that page, there may be, let's say, images. There may be audio content embedded in it. Okay? And the URL for that content will now point to one of the caches. So it won't say let's say this was cnn.com, it won't say cnn.com/image.jpg. That will cause the client to go back to the server, but instead the CNN site in this case has changed the URL to cdn.com/image.jpg. So that will cause the browser to automatically go to a CDN server to get that content. Okay, is that clear? That's the first thing. You have to change the URLs in your content to point to a cache explicitly rather than pointing to the origin server. Now, having done that, okay, the CDN has to decide which of its many thousands of caches is going to give you your content. Okay? And that is essentially done through what is called a smart DNS lookup. Okay? So what is going to happen is if you have, let's say, a URL like this, okay, cnn.com newsvideo.mp4, that's a video that you embedded, but you will actually change this to cdn.com something, right? So now that cdn.com is just a network of many proxies. You have to decide which one to use. Okay? So what you will do, okay, is you basically put intelligence in the DNS server. The client will try to find an IP address because when you have any name, it has to first translate that to an IP address. Okay? So you have to take cdn.com and say, what IP address do I use? Okay? What the DNS server will do is it will actually check where is the client located, where is this request coming from to make an IP address translation. Okay? If this, let's say the location, the request came from Amherst, it will say, is there a proxy cache nearby in Amherst? And it will send you an IP address of a nearby server. Okay? If some other user tries to ask for that exact same web page, but that user is located elsewhere, the DNS server will give it its client a different IP address, which will send that user's browser to a different cache. Okay? So this way, the DNS resolution is actually directing you to a nearby cache, and that is a special DNS server that the CDN uses. Okay? DNS, I hope you know what it means. DNS servers, DNS stands for domain name service. Okay? All that DNS does is every time you have to take a URL with a name, host name, you have to translate that on IP address to connect to that IP address. That's the job of the DNS. You just do name lookups. You say, what's the IP address of umass.edu? It'll give you an IP address. You'll say, what's google.com? It'll give you an IP address. Usually the IP address is static. Okay? That's the name of the server. Okay? Here we use that lookup to play some tricks. We said we will decide where the user is coming from. The answer will change based on where the location of the user is. Okay? Rather than, let's say, google.com, doesn't matter who is looking it up. You get the same IP address at Google servers. Okay? But here we will change that to look for the location and send that user to the nearest cache. And that way, that cache is going to send the content back. And different users in different parts of the world will connect to different caches that are located close to them and get the content. Is that clear how this works? Okay. So that's basically the idea. That brings us to what is called CDN request routing, which means CDN gets a request, how does it handle it? Right? So because you need to send the user request to the nearest cache so that they get the lowest latency. Okay? So there are two levels of load balancing the DNS is going to do. One is called global. Okay? Global load balancing is to say which location cluster should I use. Okay? That's what I just talked about, use DNS. And then once you say, I'm going to send it to this cache, that's not usually a single cache, it's a small cluster of servers. So you use what is called a local load balancer saying which server in the cluster to use. Okay, so two levels. First is you do a DNS lookup that says which cluster of cache should I go to, which location. And then once I send the request there, then there's a local load balancer saying there are many servers, which of the servers, each of them is a cache, which of the servers should I? Okay. So the global load balancer and the local load balancer. For the global load balancer, DNS-based approaches are common. Okay? You have a special DNS server which checks the location of the client that's trying to do that lookup, trying to get the IP address, and then gives you an IP address of the nearest server or the cache. Okay? And different users get resolved to different edge. So that's basically how it's all transparent. Your browser doesn't actually need to know that there's a CDN or anything like that. It just gets content. Sometimes it goes to real server, sometimes it goes to cache. Okay? So these are all issues that you have to decide. where is the closest proxy. It requires you to do what is called geolocationing of users. Okay, from the all you know is a user with this IP address is made a lookup. Okay, is trying to find the IP address of a server. From that IP address of the client, you have to find its location. Okay, that's called geo IP locationing. Okay, you're not using GPS location. Your laptop is not sending a GPS location when you do DNS lookup. So you don't really know the physical location. You have to guess from the IP address what the location. Okay? And typically you can make good guesses because IP addresses are assigned to organization. Right? So you can have 128.145 range is assigned to UMass. So if you get a request from that prefix, you know that must be located in Amherst most likely. Right? So you can use these IP address prefix ranges to make good guesses of where the user might be located and then send them to a nearby cache, okay, using DNS. So that's one thing. The second thing is, how do you do cache consistency in this case? That's because you have cached all this content. How are you doing consistency? So in this case, consistency is the responsibility of the content provider. The CDN doesn't do anything at all. It's neither going to use a proxy-based approach, nor is it going to use any other approach. Because if the user, not the user, the content creator changes the web page, they simply go to the HTML page and just change the links to whatever it is. Let's say the image changed. It's a news website. Okay? Your front page news on your website has a different image. You just change the HTML page with a different image. The next time the user gets that page, that's just going to point to a different content in the cache, not the old content. So you are not explicitly doing anything in terms of cache consistency within the CDN itself. This is the responsibility of the content provider to provide the right links so that you always get the right content. You don't want to provide old content might still be cached. Okay, eventually the CDN will purge it because it's not being accessed. Okay? So you don't need to worry about that, but you don't want to point any users to older content. Is that clear? Okay. So it's still active area of research. Lots of work still being done on how to design CDNs well, how to do caching and so on. Okay, but I'll leave it at that and talk a little bit about edge computing in the last 2 or 3 minutes. And then we'll come back to this in a later class when we have some more detailed discussion of this. Okay, so what the one thing I did want to mention is mobile edge computing. I mentioned this already. Okay, so in the mobile computing world, you always have devices that don't have enough capacity for processing heavy duty applications, or they don't have enough battery life. But in today's world, augmented reality, virtual reality, which is called AR, VR headset, that's the popular use case. Many years ago, they were phones. Well before that, they were laptops, and laptops were not powerful. So regardless how technology evolves, there are more powerful mobile devices and less powerful ones. For less powerful ones, it's always a good idea to use edge computing as a way to augment their resources. Right? So today's smartphones are capable, okay? But even their phones have smaller mobile GPUs. Right? Now AI is becoming popular. So if you're starting to deploy AI models on phones, okay, maybe the GPU is not adequate to run a big model on a small phone. In this case, you could essentially use a nearby edge server, which has a more powerful GPU, and run your inference on that device rather than on the small mobile GPU you might have. So even with phones that are more powerful, you can do offloading of, let's say, AI-based services. For AR, VR, you can offload graphics processing, which is heavy duty, to a nearby server and so on. Okay? And as a lot of these cellular networks are beginning to evolve to 5G and then 6G and so on, what is happening is many of the cell phone companies are beginning to deploy servers near cell towers. Okay? So your phone in the future world would then just go to a cell tower and use a server that's right there to do some compute. So you don't even have to go far. So your edge servers are one hop away. So your phone is directly talking to a tower. There's a set of servers sitting right next to tower. So that is what cell companies think is the future of edge computing. Cloud computing companies, they don't necessarily put servers next to cell towers, but they're still pushing them closer and closer to users. So they may not be below the tower, but they'll be close to the edge of the mobile network. So still not far away. Okay? So many different companies are thinking about how to push edge resources closer to users. Okay? And as you think about new use cases like self-driving cars, that's another example. Okay, these cars have lots of sensors. They have to think about what is happening around them. They have to carry a lot of compute on the car. So all of the processing actually has to happen locally. But maybe there isn't enough compute, so you might have nearby servers that are assisting the car when it's driving. Okay, so the car is then offloading some compute to nearby edge devices and so on. So these are all future use cases for mobile edge computing. Okay? So, and there are all these new use cases that still keep coming up in the industrial automation, where your mobile robots, they have more sophistication, but they cannot carry compute with them. Or you can think of drones that are doing all kinds of processing, or not processing, sensing in the sky, but they cannot do all the processing on board. Then you have to carry a lot of compute, and then the weight and the battery life issues come in. So the drone could then offload to mobile edge servers and so on. So all these new use cases. So this is, as you can imagine, a very current area of research. Lots of interesting things happening in the case of mobile edge computing. Okay? So we'll talk more about edge computing in future class. I'm going to end it here today. We ran out of time. Okay, so let's continue next time.